Okay, I want to thank the panelists. So Elizabeth and Chris, would you please join us at the table for the panel questions and answer? And I hope Matt is still online. Matt, are you still there?
Yep, I'm still here.
Great. So as someone from the Extreme Access Group, I just love hearing that all three projects need autonomy and robotics. So I really look forward to the workshop that is, I think, in plans for between construction, and excavation, construction, and extreme access. So we have a lot of questions in Slido, and I also have a list of questions from the excavation and construction team. So hopefully this will make for a good discussion. So this is for all of you. What is the one or few specific enabling technologies that is going to make your project work and work well on the moon? So I will start with Matt.
Sure. I think some of the main enabling things will be the robotics that are able to operate at the lunar South Pole, and other things for, say, utilizing solar power, being able to transfer that power long distances. So if I have a 100 watt or 100 kilowatt array, I need to be able to route or transfer power to those things, to things that need it. And they're probably not located right next to my array.
Okay, great. Chris?
Okay. I think I'd say, honestly, I'd go with autonomy.
But what autonomy, like, and then what level do you need it for? Like,
well, what I just presented, but the I would also say, there's of course, different levels of autonomy. I think and there is you could envision doing lunar operations teleoperated, but I think that's a bit too challenging from a latency and communication point of view, and a more human operators step in or supervise robots that are mostly doing their own decisions, making steps, and occasionally step in and say, okay, change your plan and focus in a different area. So I think I'd say periodic human intervention to reset the robots to go off in the right direction. But I think autonomy would be what I think most enables what we're proposing.
I like hearing that, from the EA side. What about you, Elizabeth?
Yeah, so I think the technology that would most enable what we're trying to accomplish is actually around the robotics, the actuators and drive modules that we need to use. There are a lot out there readily available for industrial robots and for hobby robots, but there is a wide space in between there that I think has a lot of earth-based and space-based applications that we need to develop further. They're actually starting to come out in foreign countries. And so we're a little bit behind the curve there, and being able to have those types of hardware available to us would be really helpful to what we're trying to accomplish.
When you say hardware, what kind of hardware are we talking about?
The actuators and drive modules for the robots,
okay,
specifically.
Specifically, also, I assume that they would survive, lunar environments and all of that.
That would be ideal. Yes.
Okay. All right. So from Slido, we have a number of questions. So I'm going to combine two for questions for Matt. So what are, for your project, what are the requirements for your foundation? And have you thought about impacts from seismic activities like moonquakes and how that might impact your build?
Sure. Answer the second question first. We are looking at, dynamic events like moonquakes and what sort of impact it'll have on tower during assembly as well as when it's completed. So that's part of our more detailed FEA studies. And on top of that, also looking at what tilt we might end up with. Building upwards, you'll build up your imperfections and correct them as you go if you can, and see what sort of tilt you end up with, so that can impact it as well. And with that, for foundation, we were looking at the different surface level, the tilt of the surface as well that we would build from. And for the system, we would add a leveling capability, and some other similar systems have looked at how do you compensate for a 15-degree tilt if you're landing on a slope. So for us on a lander, I think we would want to accommodate that. And I've talked to Mark about what we could potentially expect from a prepared foundation, and it's going to be likely on the order of 2-3 degrees. So that's sort of what we will have to plan for contending with.
Okay. And the next question is for Chris. So I'm going to combine a couple questions again. So this is about the lunar test environment. It's a great idea to have pumice and lightweight simulant for the 1/6 gravity, but what about the rover itself? I mean, how do you simulate that? And how do you simulate the rest of the lunar environment as a whole?
Yeah.
No, you're not. Keep talking and see.
Okay, well,
Oh, there we go.
okay. Yeah, that is a good question.
Keep talking.
All right. I anticipated this question because there are two ways, two things I mentioned. One is within, there's the easy way, but then there's like explaining the rationale. Mostly, there are certain things you should do that are kind of, hello?
Yep.
That's good. Okay. All right. That certain things you maybe should do that walk before you run. So there are certain things in our test environment that are not fully lunar-like. So let's go to the basic one. One, realize we're testing on Earth in 1G when the moon is 1/6G. So that's a very fundamental difference. For the mass of the vehicle, we're intentionally keeping the mass here on a terrestrial test low, 83 kilograms total. That would be then when to have the same reaction forces when we go to the moon, that would actually be a 500 kilogram vehicle. I think a 500 kilogram version of this vehicle is actually, we up the battery mass to what we'd really prefer to have on a terrestrial test. We're actually taking away almost all the batteries. So we actually have to do frequent charging. We wouldn't do that on the moon. We'd actually take advantage of that mass and make it a very high, a very long battery charge. There's other things that should be mentioned. We're not doing anything with lighting, nothing really unique in lunar lighting, like lighting. Mostly that is to make this more of a problem about the moving regolith and demonstrating the autonomous process of this site preparation. Later, you can add in more sophisticated things like a proper lighting environment. So the answer, that get at all the questions here. The answer is we're focusing on certain problems that don't require these changes. We are dealing directly with the mass of the vehicle by making a lightweight vehicle.
Okay, so, all right, that sounds good. So Elizabeth, it's your turn. So people are very interested in your voxels. So there are also a bunch of questions about those. So they want to know what are the sizes of the voxels and what are the masses? And can you actually produce them in different materials, different sizes as you need?
Yeah, so that's a great question. The voxels that we used in this ground demonstration, I would say are roughly a foot by a foot. They're cube octahedron shape. I don't know the exact mass. They're very lightweight. And they have been made in other shapes and sizes. As you saw with the wing that we demonstrated, as well as the parts that were used in Yosemite. The challenge with changing the size of them is that it changes your robots. And so if we want to be consistent with the robots that we're using, then we've got to stick to a base size and then just continue to build that and scale the number of pieces needed to create the size infrastructure that you're looking for. But clearly they can be done smaller. Some of the pictures you saw had robots that were, 6 inches maybe, but those are more expensive because you can't use COTS parts to create those types of robots. You have to customize the parts. So it's doable, just may cost a little bit more money and may require additional scales of robots to go along with them.
Okay. So another question for you is, have you consider building a model home on Earth for people to at least explore? And
oh, my team would love to build anything. We haven't talked about a model home, but there have been discussions of bridges and various things like that could be value added on Earth as well as for space purposes.
Yeah, you can consider a parallel to Legoland and have your own amusement park.
I love it.
And next question is for Matt. I'm combining questions again. So these are some. I think people are worried about the practicalities of having a 100-meter tower. So people are worried about how do you clean the solar panels when they're 100 meter up? And there was a different question. So we'll start with that. Matt, you're muted if you're speaking.
Sorry. Thank you. 100 meters up or 50 meters or higher. Yeah, we haven't looked at the ability to clean up that high, but the interfaces on the bays are climbable if we went forward and developed something that a robot that could climb them. For what we're looking at, dust lofting to that height, potentially with it being disturbed by surface activity, it could happen. I think to my knowledge, the dust density drops off fairly quickly, but it's something we should look at. Our system's mostly focused on the truss assembly, and the array is kind of a prime payload that we want to support.
Okay, so you think that the tower structure is going to be strong enough for a future, like a robot window cleaner type of
Exactly.
mission? Okay, great.
So the safety factor that we chose was influenced by Earth-based terrestrial towers that are designed for people to work on. Yeah.
Okay, so the base is for people, but you're not expecting people to climb the 100-meter towers, right?
No, so in that dynamic mass moving around the tower, and we're on Earth based, it's humans, but on the moon you'd have a robot. So.
Okay, thank you. So next question, I'm going to read directly from Slido for Chris, is regarding the vehicle bucket. Many construction projects use varied equipment like graders. How precise will the bucket system have to be regarding construction?
Okay. Well, we're working that out, but one thing that comes to mind is the finishing state of the prepared site preparation. Whole overall site is to be within 1 to 2 degrees of level, and then there is a RMS root mean squared finish of 1 centimeter. So that means it needs to be relatively few divots, and mostly very likely our grouser tracks or wheel tracks have to be removed in order to hit that requirement. And that's also compacted up to the 90% density right to the surface. that suggests maybe a centimeter requirement on bucket precision and final finished state of the surface.
Okay. Thank you. Elizabeth, this one is for you. Someone asked whether your team has reached out to the float effort for integration of the rail transport, and it sounds like it could be a good collaboration.
No, we have not, but that's a great tip. I appreciate the recommendation.
Okay. Thanks. And the next question is for all of you, for our team. So yesterday we heard about the risk from micrometeorites and debris and impacts. So how would meteorite impacts affect all three, your projects? So I'll start with Chris.
Well, in my work, this project of site preparation, I think the way I'd look at that is a new micrometeorite impact or a meteorite impact on the surface you've just prepared means you've got to go back and fix that if it's a large enough impact.
So, okay.
Yeah, and for the Armadas project and that system, it's designed to be repairable and reconfigurable, right? So if some of the structure were damaged, then you could go replace the specific parts that were damaged and continue operations as usual.
Okay. What about you, Matt? Particularly when meteorites hit your solar panels and that might impact your efficiency.
Oh, that's a good question. Point out that our project is the tower, not necessarily the solar panels. We consider that a payload. Yeah, it's having those be replaceable or degrade gracefully would be ideal.
Okay.
It's hard to say.
So you show your assembly going, things getting moved up. Do they also, can they get moved down so that things can be replaced? Is that have you thought about that ConOps?
So the ConOps that would use that would be having a hoist system that is at the top of the tower, kind of like a crane, where you could lower back down your solar array. So it's one of the two options I talked about. Either you have it pre-installed on top and it rides along the top of the tower as you assemble from the bottom, or you have a system that pulls your payload up after the assembly.
Okay. And then the next Slido, most popular question is also for you, Matt. They want to know whether you have compared the assembly, deployment, and additive manufacturing approaches for creating the tower.
So we're talking to some companies like Lunar Resources about additively manufacturing truss components. Some of the problems with the building a full tower out of aluminum that needs to be solved is the temperature gradient on the tower can be extreme from, say, the front side to the back side, depending on mutual shadowing. So you can get some dramatic growth if it's an all aluminum tower on, say, the front side. Yeah, we're talking about, in general at the moment, how do we build the truss components, and then there's a few things to solve along the way for a delivered tower, delivering the components. We would try to avoid some CTE issues with our joints being all metallic, and size our interface between composites and metals so that they don't destroy each other through the thermal cycling, but mostly making it as lightweight as possible by most of the struts or members are carbon fiber for what we're targeting for the first iteration.
So I might add on to that for you. Our team has looked a little bit at the different technologies for towers, and our understanding is that deployables are very reliable and very good for towers up to a certain size. For 100 meters, I don't think they quite get there. I think their limitation is more like 10 meters, maybe 20 meters. I'd have to go back and look at our numbers. But there are limitations to that. So it depends on what your requirements are as to which technology might be better. I have not looked at the additive manufacturing though. So I don't know what that would compare like.
Okay, thank you.
Yeah.
And
I can add, oh, she's very right. The height of the deployables are about that 10, 20 meter range. And when this inception of this project was, the deployables are limited to about that, how can we go even higher to get those longer duration illumination heights? So we're trying to use the assembly technology to fill a gap that's above what deployables can do.
okay, thank you. Next question is for Chris. Someone wants to know whether you have would an aquatic environment be suited as lunar gravity analog for robotic engineering construction purposes?
Yeah, well, I do think about that kind of thing, like other unique environments we could use. Yeah, I have thought about that. You know, of course, you could make a buoyant vehicle that actually has an effective reaction force in the ground. Its weight is when it touches the bottom of a surface in an aquatic environment could have 1/6 gravity. But there, I think the biggest challenge would be the material you're interacting with now is entirely different. So I think, you know, we do have, you know, there are habitats, there is work done in the big tank at Johnson, and then in the ocean out in Florida. But there are that, but they're great for certain things. I don't know that this works here for a regolith movement focused project.
Okay, so we have 1 minute left, so I want to ask the final question since this is, and if we didn't get to your questions on Slido, we will hopefully get them from our panelists later and send them out to you. So I am going to ask since this is you know, we're talking about NASA and we consider risk a big issue, right? So for all of your projects, what do you consider is the biggest risk? So I'll start with Elizabeth.
So I would say it's probably the adoption of the technology. I think that is our biggest challenge going forward for a lot of these new technologies. And so with our technology, there's nothing to compare it to exactly. So you're really comparing apples and oranges because it's new and it's different compared to what NASA has previously done. And so finding what the right information and right data is to convince someone to use the technology is probably our biggest challenge and risk.
Okay, Chris.
All right. Well, I like that answer because I think one part is ensuring there's a demand for technologies, and that's essentially what you're talking about. But if I go with a technical one, I'd say the long-term performance of our mechanisms in the presence of dust. And that's another area with our test we're not going to address at all. That's just it's presumed we can develop in time the gearboxes, the motors, the other mechanisms that will survive in the dusty environment.
Okay, Matt, you get the final word. Matt, if you're speaking, you're muted.
Yeah, sorry, I'm sorry, I was typing in chat. What was the question again?
Yeah, so what do you consider for your project as the biggest risk?
Yeah, so being able to fit on a lander and find the right place to be manifested is a big one at the moment. You know, we're lower TRL we're low TRL, and being able to prove our system and bring that TRL level up to get that adoption and infusion is something I would echo as a big risk. You know, convince folks that this truss assembly approach is the way to go for building something tall, as well as something to adapt into a more generalized truss assembly technology.
Okay, great. Thank you. This ends our session, and I want to thank our panelists for great presentations.